Hello, folks. Welcome to which part is this? Part 13 of learning Rust from scratch. And we are going to be looking at the data types chapter this time. Data types section in the third chapter this time. So, every value in Rust is of a certain type, certain data type. So, which tells Rust what kind of data is being specified. So, there's always a data type. Every value has, or every data or every value has a type or it's a certain data type. It's of a certain data type. So it tells us what kind of data or value is being specified. So it knows how to work with that data, like how to do operations on it. Like let's say if it's a number, you can operate on it by doing addition, subtraction, multiplication, division, and all that stuff. While if it's a string, then you can do appropriate string operations like concatenating the string with another string in one. So trimming the string, cutting the string, slicing the string and whatnot. So we look at two data types, subsets, scalar and compound. Keep in mind that Rust is a statically typed language, which means that it must know the type of all the variables that compile them. So whenever you're compiling, Rust should know the value or the data type of the value or the data type of the data. So every value, every variable should have a type and it should be known. So the compiler can usually infer what type you want to use based on the value and how we use it. Right. So in cases when many types are possible, such as when we converted a string to a numeric type using parse in the comparing the guess to the secret number section in chapter 2, we must add a type annotation like this. So if there are multiple possibilities, it's important to add a type annotation. So yeah. So if you don't add, then the default is taken up. I think shown as receiving code, Rust will display the following error, which means the compiler needs more information from us to know which type we want to use. Okay, great. So it says type annotation is needed. Type must be known at this point. So yeah, I mean in parse, either mention the type in the parse or in type annotation. So cannot satisfy this. Consider giving guess an explicit type or their colon and then type, right? Uh, so you'll see different type annotations for other data types. So a scalar type represents a single value. Uh, Rust has four primary scalar types. Okay, integers, floating point, numbers, booleans, and characters. That's multiple. One, two, three, four. Okay, yes, it's four. Integers and floating point numbers, so those are the number stuff, and then booleans, that's just two values, and then characters, that is just part of strings. So you may recognize these from other languages. Let's jump into how they work in Rust. Integer types, so an integer is a number without a fractional component, so there's no decimal point. So we used one integer in chapter 2, the unsigned 32-bit. Unsigned is basically the positive 32-bit integer type. This type declaration indicates that the value is associated uh, the value it's associated with should be an unsigned integer. Signed integer start with I, end with instead of u. Okay, so um, what else? And that takes up 32 bits of space. Table 3.1 shows the built-in integer types in Rust. So there must be 64-bit and 32-bit. Um, Signed, that is as in signed and unsigned together is I. So oh it's 8-bit. Oh, there's actually 60, or I forgot about that. There's actually 32, 64. There's also 128-bit interestingly, and then there's I don't know what is R. Architecture I size. Depending on the architecture, is it? I'm not sure. So 8-bit, this is, you know, 16, 32 is this double size as it goes on. So we can use any of these variants to declare the type of an integer value. Each variant can be either signed or unsigned and has an explicit size. So signed and unsigned refer to whether it's possible for the number to be negative. So in other words, whether the number needs to have a sign with it, signed, or whether it will only ever be positive and can therefore be represented without a sign, that is unsigned. So it's like writing numbers on a paper. When the sign matters, a number is shown with a plus sign or a minus sign. However, when it's safe to assume the number is positive, it's shown with a no sign. are stored using two's complement representation. It's interesting. So there is a different kinds of representation. So looks like they are stored using two's complement representation, signed numbers. So each signed variant can store numbers from minus 2 power n minus 1 to 2 power n minus 1. That is n bits inclusive, where n is the number of bits, right? That variant uses. So an 8 bit can store 8 minus 1 to plus 7, right? So minus 2 plus 7 to 2 plus 7 minus 1. Um, so which equals minus 128 to 127, and unsigned variants can store numbers from 0 to 2 power n minus 1. So like half the numbers basically over here. I mean, here you can see it's the same number of numbers, right? Same. I mean, the range size is same. Um, so here you can actually see the range size is a bit like, I mean, different in the sense that bigger range because it starts from zero, so it's different. So yeah, and one moment, so let's do two, two, yeah. The number of numbers is still 2 per n minus 1, I think. So unsigned 8-bit can store numbers from 0 to 2 per 8 minus 1, which is like 255, 0 to 255. So additionally, the I size and U size is, signed size and unsigned size. It depends on the architecture of the computer your program is running on. So which is denoted in the table as ARC. 64 bits if you are in a 64-bit architecture, and 32-bit if you are in 32-bit architecture. You can write integer literals in any of the forms shown in table C2. So note that number literals that can be multiple numeric types allow a type suffix, such as 57 unsigned 8-bit to designate the type. So so you can do a type suffix. So the number literals can also use underscore as a visual separator to make the number easier to read, such as 1 underscore thousand, which will have the same value as if you have specified thousand. So and integer literals in trust, so decimal points. So 98 underscore triple two and hex. I don't know why this is called decimal. Okay, this is normal 10 base 10, and hex, that is base 6, 0xFF, octal base 8 numbers, so 0O 77, and then binary ones and zeros, so 0B binary, and then bytes B, and then A. So single characters, I believe. So unsigned 8-bit only. So it's 0 to 2, I think. So that's kind of like ASCII. So how do you know which type of integer to use? If you're unsure, Rust's defaults are generally good places to start. Integer types default to you know signed 32-bit. The primary situation in which you'd use I size or U size is when indexing some sort of collection. So indexing, interesting. So integer overflow. So let's say you have a variable of type unsigned 8-bit that can hold values between 0 and 255. So if you try to change the variable to a value outside the range, such as 256, integer overflow occur which can result in one of two behaviors. When you're compiling in debug mode, Rust includes checks for integer overflow that can cause a program to panic at runtime if this behavior occurs. Rust uses the term panicking when a program exits with an error. We'll discuss panics in more depth in the unrecoverable errors with panic section in chapter 9. Okay. When you are compiling in release mode with a release flag, Rust does not include checks for integer overflow that cause panics. Instead, if overflow occurs, Rust performs two's complement wrapping. In short, values greater than the maximum value the type can hold wrap around to the minimum. So it goes to the next side. To the minimum of the values the type can hold. In this case, in the case of a unsigned 8-bit, the value 256 becomes 0, the value 257 becomes 1, and so on. The program won't panic, but the variables will have a value that probably isn't what you are expecting it to have. So in debug mode, it panics, but then in release mode, it just does a two's complement wrapping. So relying on isn't what it is. So relying on integer overflows wrapping behavior is considered an error. To explicitly handle the possibility of overflow, you can use these families of methods provided by the standard library for primitive numeric types. Wrap in all modes with the wrapping methods such as wrapping add. Return the none value if there is overflow with the check methods. So return the value and a boolean indicating whether there was a overflow with the overflowing methods. So saturate at the values minimum or maximum values with the saturating methods. So floating point types. So Rust also has two primitive types for floating point numbers, which are numbers with decimal points. So Rust floating point types are 32-bit and 64-bit, F30s, so which are 32 bits and 64 bits in size, respectively. The default is 64-bit because on modern CPUs it's roughly the same speed as 32-bit, but is capable of more precision. So all floating point types are signed. So here's an example that shows floating point numbers in action. So you have 3.0, 2.0, and all that, and are represented according to the IEEE and FIFO standard. Okay. Numeric operations, suppose the basic mathematical operations you expect for all the number types: addition, subtraction, multiplication, division, and remainder, which is the modulus sign. So if you run this, I think you should not have any results because no output here. I can probably just change the code, but I'm not able to change it here interestingly. And so this is 15, this is 91.2, this is 120, this is tricky. So this results in so it gets truncated. So this results in this one is three times I think. Oh no, not three times. This is not three times. This is one time something. And this is minus one. So remainder and this is three. So each expression in these statements uses a mathematical operator. So and evaluates into a single value, which is then bound to a variable. Appendix B contains a list of all operators that trust words. So you have caret symbol. They have not. These are the operators not for a macro expansion, and then bitwise or logical complement not if you give beforehand, and then not equal to expression is not equal modulus arithmetic remainder, and then modulus equal to is equal to the modulus value. So arithmetic remainder and assignment. So plus equal to means equal to and then add arithmetic addition and assignment again. So, and this is borrow. This is example is mutable time, mutable borrow, not, and then this is borrowed pointer type. Okay, this is borrow the expression. This is the type for types borrowed pointer type, and this is bitwise and so put it between bitwise and an assignment. This is and logical and short circuiting logical and so if the first one is zero, it doesn't go to the next one. First one is one, it does go to the next one, and then there's short circuiting or also again. Let's see. Multiplication and an assignment, and then dereference, raw pointer, traits, compound type, constraint. I wonder what that means. Trait plus trait. So you should implement all these traits, I guess. So and then addition, an assignment, argument, element, and element separator. Okay. So this is negative arithmetic negation, subtraction, an assignment, and then this is the return type function and closure return types. And then I think this is closure. And then this is dot member access, okay, dot, and then dot write exclusive range literal. So if you have dot write exclusive dot thing, so doesn't include the right thing. So equal to, so write inclusive range literal. So if it includes the equal, then it's write inclusive range literal. Struct literal update syntax, okay. Um, Variance, interesting. There's a lot actually. Namespace part, interesting. Cool. So I will look through this and continue with Boolean type and the character and compound types in next video. I'll see you in the next one. Bye bye.